Hello everyone, my name is Signolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, hello. In this video, we are going to be looking at inverse functions. Okay, so we looked at different functions. We looked at the parabola. We looked at the exponential functions throughout the course of my videos. And you would have looked at different other kinds of functions like the straight line and the hyperbola in your earlier grades. What we're going to be looking at right now is the inverse functions, and particularly we're going to be looking at the inverse functions of the parabola, the exponential function, and the straight line, and what they are and how to deal with them and how to find the inverse functions. Okay, so you will recall that when we were doing functions, right, you would start off with a certain x value. You would start off with a certain x value. That's the value that you would know from the get-go, from the onset, right? You would usually, if you were to use a table method, for instance, you'd have x here and you have y here, and then you'd have those values this side, right? And then you would use these values to find your y values, your corresponding y values. Okay, that's what we've been doing up to this point for your functions and for your normal functions. Okay, now we ask ourselves, can we start off with a y value and, having a given y value, find out from which x value that y value came from? That is the whole point of us doing inverse functions, right? We want to start off with our y value and we want to find out from which x value that y value comes from. Okay, and this is what we're going to be basically doing. In essence, we are making our y the independent variable and we are making our x the dependent variable, whereas we know that for functions these two things are reversed. Okay, so let's hop right into it. Okay, so the three functions that we will be looking at are the parabola, we will be looking at the exponential function, and we will be looking at the straight line function. Okay, we'll be looking at those functions and we will be finding their inverses, and we'll be pointing out a couple of important things as we look at these graphs. Okay, so first and foremost, remember what a function is, right? Remember what a function, we covered what a function is in the very first video that we prepared for these lessons on functions, right? A function, the main characteristic of a function is that it has one unique, a function has one unique y value for one or more x values. One unique y value for one or more x values. I'm just going to quickly explain what that means again, but I did explain it in the first video that we did on functions. Now, if you've got, let's say, an instance, for instance, a parabola that looks like that, we can use the vertical line test. Remember, the vertical line test is that you just draw a vertical line, and each time you draw a vertical line at any location, your graph should only be intersected by that vertical line at only one point, and that's how you are able to tell if a graph is a function or not. So if I draw a vertical line at that point, the only intersection is at that point. If I draw a vertical line at that point, the only intersection is at that point. If I draw, so I must have only one intersection between the vertical line that I draw and my graph itself. That tells me that I have one y value that corresponds to that point. Okay, now this is in opposition to if I have, say, something like this, where I've got my Cartesian plane that looks like that, and I draw a graph that looks like that. This is my graph, and I draw a vertical line. When I draw a vertical line, I see that there's 2 points that intersect the graph. Therefore, this is not a function, because I've got 2 points that are intersected by the vertical line. Okay, so this is what I mean when I say a function is a graph that has one unique y value, for one or more x values. In this case, the x value that this is the y value that we're looking at for this line, and this corresponds to this x value. It corresponds to this x value, but it also corresponds to this x value. Okay, so these two x values can give me the same y value here. Okay, and in this instance here, I've got a y value there and I've got a y value there, but those two y values, this y value and that y value, can be given to me by that x value here, by this x value there. This is why this is not a function. Okay, so a function is a graph whose y values are unique. They can only be one y value. They can only be one y value for one or more x values. Okay, but they can never be more than one y value for the same x value, or for more than one x value. Okay, so this is what a function is. We covered this in our first video, and if you're having any difficulty following or understanding this, then just quickly visit the first video, and it should bring a bit more clarity on this. Okay, so back to inverse functions. Now, for inverse functions, what happens, remember, what we're trying to achieve is that we are trying to make our y the independent variable. We're trying to make our y independent variable so that we can find the x value that y comes from. Now, your inverse functions follow a simple procedure. It's mathematically it's a very simple procedure for you to find the inverse function. And what you do to find an inverse function is essentially, okay, let's just say how to find an inverse. Before I get to my examples, how to find the inverse, the inverse of a function. How to find the inverse of of a function given an equation, right? Given the expression, given an equation, question mark. How do you find the inverse of a function given the equation? Well, let's look at a couple of equations. Let's say the equation that I gave you, let's say the function that I gave you is f, or let me just call it y. Okay, you've got y is equal to 3x squared. Okay, this is the equation that you're given, and we ask you to find the inverse. Find the inverse. Find inverse of this. Well, to find the inverse, you just interchange the x and the y. You just interchange the x and the y. So where you have an x, you put in a y. When you have a y, you put in an x, and then you make y the subject of the formula so that you can work with the equation easily. Okay, so the inverse of this equation, if I were to ask you to find the inverse of this equation, what you would do is you would say x, okay, where you have a y, you put in an x. So x is equal to 3y squared. Okay, that's all you do. Here you have a y, here you have an x. You interchange the two. Here you have a y, here you have an x. You interchange the two. Okay, and then once you have this, then you make y the subject of the formula. So if you gotta make y the subject of the formula for the inverse. So when you make y the subject of the formula, you just divide both sides by 3. So divide both sides by 3, and let me scroll down. Okay, when you divide both sides by 3, what do you have? You've got x over 3 is equal to this 3 and that 3 cancel each other out, so you've got y squared. Okay, and then you've got so I'm just gonna switch them around because it's easier for me to work with them like that. So you've got y squared is equal to x over 3. Okay, and then you just take the square root of both sides so that y is your subject of the formula. So you've got the square root of x over 3, and then this could be plus or minus. Okay, and this is your inverse. Now, why am I adding that plus or minus? Just remember that if you've got 4, right? If I ask you which number do you have to square to get 4, you will tell me that, okay, you have to square 2. 2 is the number that you have to square to get 4. But I can also square negative 2 in brackets. Negative 2 can give me 4. So therefore, the square root of 4 is equal to plus or minus 2. Okay, it's not just 2. And this is why I've got these negatives here, right? Because y squared can be given by this expression squared, but it can be either positive or negative. Okay, so that's why. Okay, so that's easy. That's it. That's all you have to do to find the inverse given an equation. Let's do another quick example. Let's say you've got y is equal to x plus 3, right? This is a straight line, and I ask you to find the inverse. Okay, find the inverse. That is what we are required to calculate. Find the inverse. Easy. You just interchange the letters. Where you have y, you put in an x. Where you have an x, you put in a y, and then you've got plus 3, and then you make y the subject of the formula. So the 3 will go to the other side and it will change its sign, right? So you've got x minus 3 is equal to y. Or if I can switch them over, I like to have my y on my left hand side, so that's going to be x minus 3, and that is your answer. Okay, that is how you find the inverse. Let's do another quick example. If you've got y is equal to x squared plus, or let's say x squared minus 4. Now ask you, find the inverse. Find the inverse of this equation. What will you do? You just interchange the x and the y. Where you have a y, you put in an x. Where you have an x, you put in a y squared minus 4. Okay, and then you have to make y the subject of the formula. So you're going to say x plus 4, because this 4 goes to the other side and it changes its sign. Okay, it goes to the other side and it changes its sign. Then you've got y squared. Then you take the square root of both sides. Then what you will have ultimately is plus or minus the square root of x plus 4. Okay, let's do one last example. This one is going to be a bit complicated. What if they ask you to find the inverse of y is equal to 3 to the power of x? This is an exponential now. Okay, they ask you to find the inverse of this. What do? Well, let's just put down the RTC they're required to calculate first, or they're required to find. Okay, what is the inverse? Well, same thing, same procedure. You just interchange the variables. Where you have y, you have x, and where you have x, you're going to have y. So this is going to be x is equal to 3 to the power of y. Right, and now you have to make y the subject of your formula. How do you make y the subject of your formula? Well, you use logarithms. Okay, you will have to visit a different video on the laws of logarithms for you to fully follow what I am going to do. But you use logarithms to make y the subject of the formula. So how do you do that? Well, first step is to just put logs on both sides. So you're gonna have log of x is equal to log of 3 to the power of y. Okay, you just put logs on both sides. Because I had x here, I had x here, I had 3 to the power of y there, I have 3 to the power of y there. So all I did was introduce logs. Okay, so once I've introduced my logs, then I can simplify further. Then I have log x is equal to this y can become the coefficient of that log there. So this is going to be y times log 3. Okay, and then you make your y a subject of the formula. You just divide both sides by log 3. So you're going to have log x divided by log 3. Log x divided by log 3, which can be further simplified to log x and then base 3 there. Okay, and then this is going to be your answer. This is going to be your inverse equation. Okay, So that's all you do. So basically, for you to find the inverse of an equation, you just interchange the variables, the x and the y. Where you have an x, you put in a y. Where you have a y, you put in an x, and then you make y the subject of the formula. Okay, and I will prepare a separate video where I'm explaining laws of logarithms. Okay, now all of this was finding the inverse of a graph given the equation, or the inverse of a function given the equation. How do you find, what if they ask you to find and sketch the inverse of that function? Okay, sketching inverse functions. Sketching inverse functions. Sketching inverse functions is what we are going to do next. How do you do that? Well, let's start with the straight line. Okay, straight line is the simplest, it's the easiest. Let's start with the straight line. If I've got a straight line, here's my Cartesian plane here. Got my Cartesian plane, and I've got, say, my straight line. Straight line is y is equal to x plus 1. Okay, let's call it y is equal to x plus 1. Okay, how will that look? Well, let's quickly sketch what that graph will look like. We know that the x-intercept when y is equal to 0, the x-intercept when y is equal to 0 is going to be 1, so minus 1 will be there somewhere, right? The y-intercept when x is equal to 0 will be 1, so y will be somewhere there. So the graph will pass through both points, and it will look like that. Okay, it'll do that. That's my graph, quickly sketched. Okay, this is my graph, and now what is the inverse? What is the inverse of this graph? I'm going to write the inverse in blue. Remember how to find the inverse. The inverse, I just interchange the variables, and I make y the subject of the formula, right? I make y the subject of the formula, so therefore this is going to be y is equal to x minus 1. Okay, so that's the inverse. The inverse is y is equal to x minus 1. I'm going to erase that, and I'm going to keep the inverse here. Okay, now how do I sketch that inverse? Well, let's quickly find the intercepts. Okay, so when x is equal to 0, y is equal to minus 1. Y is equal to minus 1. Right, okay, let's put it a bit further down there. Y is equal to minus 1. And when y is equal to 0, x is equal to plus 1, right? Plus 1, so it's going to be somewhere there. That's 1. Then the graph will pass through those 2 points. It'll do that. Okay, the graph will do that. It's a straight line. Now, what do you notice about these lines? These lines are in, so this one, this black line is the inverse of the black line, of the red line, sorry. The black line is the inverse of the black line. Now, I want you to notice that these lines are mirror images of one another. They are mirror images of one another. These lines look exactly the same. If you look at them, they look exactly the same. They're parallel to one another. They look the same, right? So this tells you that they look identical and they are mirror images of one another. But where's the mirror? Where's the mirror? Okay, so the mirror, if it so happens that these two are mirror images of one another, then the mirror can only be in between them. The mirror can only be there. Okay, the mirror can only be there. There's the mirror there. Okay, there's the mirror. So this red line is looking at itself on the mirror, and it's seeing that black line there. So it's reflected about that line there. And what is this line? What is that line? Well, this line is the y is equal to x line. This is y is equal to x. Okay, that's the equation of that line. Y is equal to x. Okay, and it so happens that, okay, when we find the inverse of functions, the inverse will be a mirror image of the function that we started off with, and the mirror will be this y is equal to x line. Now, why is the mirror this y is equal to x line? How can it be? Why is it? Remember how we go about finding the inverse of a function. What we do is we interchange the x and the y, right? Where we have x, we put in y. Where we have y, we put in x. So when we interchange, if you remember from earlier grades, when we interchange the x's and the y's of an equation, we will end up with a reflection of the equation of the graph on the y is equal to x line. Okay, on the y is equal to x line. That is basically one of the laws of reflections that you would have covered in earlier grades. Okay, so this takes us to our first important piece of information about, or at least second. The first piece of important information was that to find the inverse, you interchange the variables. So the second piece of important information is that when you find the inverse of a graph, that inverse that you get is a reflection of the function that you started off with about the y is equal to x line. Okay, that's the second piece of information. Now, that was the straight line. Let's look at another straight line. If I've got my Cartesian plane there, and I'm just gonna draw out a random. I'm gonna draw a random line that looks like that, right? And I ask you to find the inverse. To find the inverse of this line, what are you going to do? Well, if I ask you to quickly sketch it, no calculations, just quickly sketch it for me. Well, what you're going to do is I want you to draw in your y is equal to x line. Draw in your mirror, okay? Draw in your mirror, and your mirror, just try to draw it in as accurately as possible. So it must be 45 degrees. That is 45 degrees to the horizontal axis and to the vertical axis. Okay, so it's got to be 45 degrees. So once you draw in your mirror, then you can draw in the reflection of the graph that you started off with along that mirror. Okay, so now you've got all these points. All these points make up this graph. All these points make up this graph. All of them, right? This graph is made up. Remember, graphs are made up of coordinates, and coordinates are essentially points, right? So for you to find the reflection of this graph, you've got to reflect each one of those points. Each one of those points you've got to reflect about the y is equal to x line. So how do you do that? Well, that is that line there. Your x here becomes your y, and your y becomes your x. Right, your x becomes your y, and your y becomes your x. So this is a negative x. You can see that that's a negative x there. So where's your negative y? Your negative y is going to be somewhere there, down here. And that's going to be your positive y is going to be a positive x is going to be somewhere there. So this is going to be somewhere here. Okay, so turns out that the way I drew out this thing is almost at 45 degrees. But anyways, so you've got that there. So your negative x here, whatever the number is, your negative x there becomes your negative y there. That number becomes that number. Okay, that's all that happens. That number becomes that number. Remember, you're flipping the two around. Same thing for this thing here. That same thing for that point there and that point there. That's gonna come up to somewhere there. Then that's gonna happen, and that's gonna happen, that's gonna happen. And then you will see that as you plot all the points, what you're gonna end up with is something that looks like that. Okay. Now this is a mirror image. The red line is a mirror image of the black line. Okay, so that part there is the mirror image of that part, and this part there is a mirror image of that part there. Okay, so that's essentially your inverse. Okay, if sketching it this quickly is complicated for you, do it point by point, right? Find the coordinates of the graph, or find actual coordinate points and then plot them. Okay, and then you will get your answer. Okay, so that's essentially how you find the inverse. Okay, so let's do it for your firstly, before we move on to other types of graphs, I want you to notice that we still have a function here. The inverse is still a function. So if we perform the vertical line test, right? If we perform the vertical line test on just the inverse. So here I'm going to remove the original graph. I'm going to remove the original graph, and I'm only just going to be left with the inverse. If I do the vertical line test, if I draw a vertical line, the vertical line only intersects the inverse at one point. It doesn't hit the inverse function at any other point. It only hits it at one point. So the inverse is still a function. You see that? It's still a function. Okay, so we're safe. Vertical line test at that point, doesn't matter at which point you draw it, it's got to hit the inverse at one point for the inverse to be a function. Remember, We are dealing with functions. A function only has one unique y value. So even an inverse function is still a function. It has to be a function. So it has to retain the qualities of a function. Okay, so that is what I wanted to point out. Let's move on to the parabola. Okay, let's move on to the parabola. Now, let's say you've got a parabola. You've got a parabola that looks like that. That looks like, okay, it's given by y is equal to 3 to 3x squared. It's given by 3x squared. Okay, now you will tell me that this parabola looks like this. You will tell me that this parabola looks like that. Okay, it looks like that, and it goes through the origin like that. And if I ask you to find the inverse of this parabola, I think we found it earlier on. We found the equation earlier on. That equation was, let's just try to find it quickly. Is this it? 3x squared. So the is x, it's the square root of x over 3. Square root of x over 3. Okay, so the inverse is, let's write the inverse. The inverse of this function, I want to say y inverse, is equal to plus minus x over 3, x over 3. By the way, this is how you show that something is an inverse. You put in that prime sign there, that apostrophe there, you put it in. It's just to indicate that this is the inverse of a function. So if somebody looks at this, they will know that they're looking at the inverse of some function. Okay, now how does the inverse of this function look? This is the blue equation here. How does that blue equation look? If I were to sketch it out, how would it look? Now, remember, the inverse is a reflection about a mirror, about that mirror there, right? About that y is equal to x mirror there. Okay, so it's a reflection about the y is equal to x mirror. Now, if I were to reflect this graph, the red graph about that mirror, then what I would have is an equation in blue that looks like that. Okay, that looks like that. This is a reflection of that graph. Okay, it's just if you were to do it point by point, you would see that you would end up with a graph that has that shape there. Now, it's simply a reflection. You can do it point by point. You can get the equation and then substitute different values of x so that you get different points. And then when you combine those points, you will see that this is the shape that you will get. But we have a little issue now here. We have a little issue. What is the issue? Well, we don't have a function anymore. Let's do a vertical line test. Firstly, I'm going to remove the red graph, and then I'm going to do the vertical line test on this graph that we have here. If I draw a vertical line, look at this. I've got my graph being intersected by my vertical line at 2 points. I don't want my graph to be intersected at 2 points, because what does that do? It makes this thing not be a function anymore. Remember, in order for this to be an inverse function, it must retain the quality of what a function is. A function does not fail the vertical line test. Okay, if I draw in another line there, look, it's 2 points that are being intersected. It can't be 2 points. It has to be 1 point. For this thing to be a function, it has to be 1 point. Okay, so how do we deal with this problem? How do we circumvent that little dilemma? Because we want the function. What we started off with was a function. A parabola is a function, right? A parabola is a function because it does not fail the vertical line test. But the inverse of a parabola fails the vertical line test. So how do we circumvent that problem? Well, this is when we do what we call restricting the domain. Okay, so we will have to restrict the domain. Restricting the domain. Now, before I tell you what restricting the domain is, I just have to explain what it is, what a domain is. So a domain, I'm going to explain what a domain and a range is, right? So a domain is basically, just to keep it as simple as possible, domain are the x values of a function. Okay, domain is the x values of a graph. Okay, x values, and the range range are the y values of a graph. The y values of a graph are the range of the graph, and the x values of the graph are the domain of the graph. For instance, if I were to draw out a Cartesian plane, and I draw out a function, a parabola like that, the domain, I'm going to call it D. The domain of this graph would be x is an element of real numbers, all the real numbers. Why? Because the graph exists. Remember, this graph goes on forever, right? The graph goes on forever. So the graph exists everywhere for every value of x. For every value of x, the graph exists. For every value of x, the graph exists. Okay, for all the values of x, the graph exists. Now, that point there is my y-intercept. Let's say my y-intercept was 0 and -4. Now, you will agree with me that if this is the y-intercept, right? If these are the coordinates of the y-intercept, then that value there is -4. Y is equal to -4. You will agree with me that for any y value that is below -4, right? For any y value that is below -4, the graph does not exist, right? The graph only moves from -4 going up. Okay, and then for -4 going downwards, the graph is not here. The graph does not exist below -4. So therefore, the range D, the range for this graph is y is greater than or equal to -4, where y is an element of real numbers. Okay, so for all the real numbers above -4, including -4, the graph exists, but for all the y values below -4, the graph does not exist. Okay, so this should have also been covered in earlier grades. I'm just explaining it very quickly and very simplistically here. Okay, so going back to restricting the domain. What does restricting the domain mean? Well, here's another piece of useful and very important information that I want you to remember regarding inverse functions. Okay, so for inverse functions, right? Let's say I draw out my Cartesian plane. I draw out my Cartesian plane like that, and I've got my parabola there. We know that my parabola is a function because my parabola passes the vertical line test. It passes the vertical line test, right? So this is a function. But we've also just discovered that the inverse of this function, which looks like that, is not a function. Why is it not a function? Because it fails the vertical line test. It fails the vertical line test. So if we restrict the domain, if we choose a portion of this original function that we are dealing with, if we choose only a portion of it to find its inverse, then we can end up with an inverse that is actually a function. So what do I mean? Let's say, okay, instead of finding the inverse of this entire function, what I will do instead is I'm just going to find the inverse of a portion of this function. So I'm just going to remove that, and I'm just going to find the inverse of only a portion of this function. So that function, remember, looks like that. I'm only going to find a portion of that. Okay, I'm only going to find a portion of this part, the inverse of that portion of the function. So this part I'm going to ignore completely. What does that give me? So if I reflect that portion, about this mirror, remember where the mirror is here. If I do that, then if I reflect that about the mirror, what will I get? What I'll get is that. This is what I'll get, okay? And then what do I have here? Well, let me erase the original function. Let me erase the mirror. What do I have here? Let's perform the vertical line test. If I perform the vertical line test, the vertical line only intersects the inverse at one point, at one location. Okay, it only intersects the graph at one location. Since it intersects it at one location each time, then this indeed is a function. But in order for me to make this a function, what did I have to do? I had to choose a portion. I had to choose a portion to reflect. Okay, now let's go back to what I had here. I had to choose a portion to reflect. Okay, remember I chose this portion to reflect, but we know that the graph in reality looks like that, right? But then I only chose this portion reflect. So I restricted my domain. Remember, my domain are my x values. So I restricted, I limited, I put a limitation on my x values so that I could be able to do what I wanted to do, right? So what was the restriction that I put in here? Well, the restriction that I put in here is I found my inverse, but for only the portion of the original function that lied in the region of x is equal to or greater than 0. Okay, because x is negative here, x is positive here, remember I chose to ignore this side, and this side lies in the negative x-axis, so I ignored it completely and I only focused on that portion of the graph. And since I focused on that portion of the graph, I could reflect that and I could get an actual inverse function. So this here is the restriction that I imposed on my domain. I restricted my domain. Okay, so that's what essentially restricting the domain is, and therefore I could get my inverse function that looks like that. Okay, now I also want you to note something very important, right? Remember that when we are finding the inverse, I think it's important to sort of write this as a nice summary. When we're finding the inverse, right, we switch or we interchange x and y values, right? And then once we do that, what happens is that the inverse is a reflection. Inverse is a reflection of function. Inverse is a reflection of function about the line about the x is equal to y line. Okay, about x is equal to y, or you can say y is equal to x. Okay, now this is another important aspect that I want you to take note of. The domain, right? The domain of your function. The domain of your function becomes the range of your inverse function. Becomes the range of your inverse. What does this mean? This means that the values of x for which your graph exists become the values of y for which your inverse exists. Okay, so if you look at this, I'm going to remove that part because we didn't use it. We don't want to use it. If you look at this, this is your original function. This is your original function. The values of x for which your original function exists are x is greater than or equal to 0. Now if you look at your inverse, in red. Your inverse is this function here in red. Where does this inverse function exist? Well, it exists only from y is equal to 0 and going upwards. So it only exists for y is greater than or equal to 0. Do you see what happened here? The domain became the range, and the range became the domain. Okay, the domain became the range and the range became the domain. So this is what happens. This is what happens when you find the inverse of a function. All right. Okay, so that is essentially what would happen. So that was the inverse of a parabola, and that is the inverse of a straight line. Now I'm going to look at the inverse of an exponential. Okay, I'm going to look at the inverse of an exponential. So if I've got the same principles apply. So if I've got my Cartesian plane there, and I've got my exponential function that looks like that, I know that the inverse of this exponential function is going to be a mirror image of this exponential function, and the mirror is this blue line here. So the red line reflected about this will look like that. Okay, try to draw it a bit more accurately than that, with the distance shown a bit more accurately from the mirror. Okay, this is going to be the inverse. How do I know this is going to be the inverse? How it looks? Well, simply because simply because I know that my mirror is that line there, and this line reflected along this mirror is going to look like that. Okay, so that's the inverse of an exponential. Actually, I did something wrong. I did something drastically wrong. I did something wrong. So remember, I spoke about inverting the x and y's, and your range becoming your domain and your domain becoming your range, right? Remember, for your exponential, this is your horizontal asymptote, right? Now, for your inverse, you're not going to have a horizontal asymptote. You're going to have a vertical asymptote. You're going to have a vertical asymptote. So therefore, your graph will actually look like that. Okay, because this is now your asymptote. Your graph will actually look like that. Your graph will approach your asymptote and never reach your asymptote. Okay, so then this is actually your inverse. You see, if you understand the principles, and if you understand the kinds of answers you should expect from the theory that you studied, you should be able to identify when you made a mistake. Okay, and throughout these videos, sometimes I will make mistakes, but I will catch them. I will always catch mistakes that I make because I understand I understand the theory, and you should be, as you're working along all your problems, you should be able to identify any mistakes that you make, because you should always be consistently checking yourself while you're working through these problems. Okay, no one is 100% perfect, and I'm not going to edit the mistakes out of these videos because I want you to see me make mistakes, and I want you to see me catch myself making those mistakes, and I also want you, hopefully, to catch those mistakes when I make them. Okay, so let's do that. So okay, so the when I was finding the equation of an exponential inverse earlier on, I had y is equal to, I had some values. Let's use another value now. 4 x, right? 4 to the power of x. 4 to the power of x. Now, since this is my exponential function, and if I have to find the inverse of this, we know that we're going to have to use logarithms. So I'm going to add logs here. This is log y is equal to log 4, and then to the power of x, and then so log y. Sorry, so to find the inverse, see, I made another mistake now. Must catch myself. What was the first step? First step is to interchange the variables. First step is to interchange the variables. So x becomes y becomes x, then it's 4, then to the power of y, then you find the logs, you put in the logs. Log x is equal to log 4, and then y. Okay, then you find your y. I'm just going to skip ahead to the answer because I just want to show you something. This is going to be y is equal to log x, then there's going to be 4 there. Okay, so now this equation here is the equation that will describe that inverse. This is the equation that will describe that inverse. Now, if you have an exponential function that is given by y is equal to a to the power of x, where a is greater than 1, then what you will have for your log, see if I got a little bit of space here. What you will have for your log is your inverse is going to be log, and then where you had your a, okay, where you had your a, that's where you had your 4 here. Your a is going to be that value there. Okay, so your a is going to be that value. So that's going to be a there, and then that's going to be your x there. This is going to be the equation of your inverse for an exponential. Okay, that's going to be your general equation for your exponential. Of course, you can add things onto this equation, and you can make amendments and whatever, just like we made amendments with all our exponential graphs. But this is the general form that your equation will look like. You can have log x base a plus something or minus something, or you can have you can have a coefficient there or whatever. All that stuff doesn't really matter. This is your standard form or your general form. Okay. Okay, so I think the important things to remember are in this page here. So for your inverses, you switch your x's and y, and then you make your y the subject of the formula, and your inverse is a reflection of your function about x and y, and the domain of your function becomes the range of your inverse function. Okay, And remember how to restrict the the domain. As a matter of fact, let me just tell you something with regard to restricting the domain. You will have to restrict the domain for parabolic functions. Okay, for parabolic functions, that's essentially where you will have to restrict the domain. But how do you know which point to restrict? How do you know where to start restricting your graph? Well, essentially, let's say you've got a parabola that looks like that. Okay, and let me try to draw it a bit more displaced. Let's say you've got a parabola that looks like that. Okay, so you restrict your parabola at its turning point. Where basically it stops repeating. So your graph, that part of your graph and that part of your graph are mirror images of one another, but you only want one portion of your graph. So whatever the x value is there, that's where you start restricting your graph from, so that your reflection is gonna be a mirror image of that portion. Okay, so you restrict it from the x value of your turning point. Okay, and then going to the right or going to the left. You can choose either side. You can either restrict it going to the right or going to the left. Okay, that's how you restrict the domain. Okay, so that's essentially inverse functions. They're very simple, they're not complicated, and that's how you would deal with them. The rest is just examples and examples and examples. Okay, but that is essentially how you deal with exponential functions. The rest is just practice. We will prepare separate videos where we are solving some examples, maybe past exam papers, and we will explain these more. Until then, till next time. Lesson number one, lesson number one. Lesson number one, lesson number one.